All right, have you ever been in a situation where you need a sorting algorithm that's not just fast, but like guaranteed to be fast? Every single time. And without hogging a ton of memory? Well, today, we're going to break down Heap Sort. It's an absolute powerhouse of predictable performance that does exactly that.
So picture this, right? You're working on a system where memory is super tight. Maybe it's an embedded device. And you just cannot afford a worst-case performance hit that grinds everything to a halt. You need speed, for sure, but you also need rock-solid reliability. So, what's the right tool for the job?
Well, that's where Heap Sort comes in. It's this really clever, in-place sorting algorithm that gives you that guaranteed O of n log n time complexity. And I mean in the best, average, and worst cases, all while using just a constant amount of extra memory. It's kind of the reliable workhorse of the sorting world.
So how does it pull this off? What's the secret? Well, it's not some complex external data structure. The magic is built right inside the array itself, in this sort of hidden tree, and we call that a binary heap.
Okay, so what is a binary heap? It's a special kind of binary tree. First, it's complete, which just means it's totally filled up on every level, except maybe for the very last one, which fills in from left to right. Now, for a max heap, and that's what we use for sorting in ascending order, there's one simple rule. Every parent has to be bigger than or equal to its kids. This one rule elegantly guarantees that the largest element is always right at the top.
And here's the really clever part. You don't need to create a separate tree object with all those pointers and nodes. Nope, we can represent this entire structure perfectly right inside the original array. It's a tree, just hidden in plain sight.
And the way we do this mapping, it's surprisingly simple. Check this out. For any element at index I, you can find its left child at 2i plus 1 and its right child at 2i plus 2. That's it. This simple math is the whole key. It lets us navigate the array as if it were a tree, and that's exactly how Heap Sort does all its work in place without needing any extra memory.
Okay, so the algorithm itself really breaks down into two main phases. First up, we have to take our messy, unordered array and arrange it into that max heap structure we just talked about. And you know what? This setup phase is surprisingly fast.
Yep. This process of building the heap, you'll often hear it called heapify. It takes just linear time, or ON. That just means the time it takes grows in a straight line with the number of items. It's a super efficient setup, and honestly, it's a fantastic detail to remember because it trips a lot of people up.
Now, I know what you might be thinking. Hold on. If moving stuff around in the heap involves logarithmic operations, shouldn't building it for n elements take O of n log n time? And you know what? That's a totally fair question. But the answer, surprisingly, is no.
The magic here is that we build it from the bottom up. We start fixing that heap property from the very last parent node and work our way up to the root. And if you think about it, it makes perfect sense. Most of the nodes are crammed into the lower levels of the tree, right? They only have to sift down a really short distance, or maybe not at all. It's only that single node at the very top, the root, that might have to travel a full height. So when you do the math and add it all up, the total work stays impressively low.
All right, so our max heap is built. We now have an ironclad guarantee. The biggest element in the entire array is sitting pretty right at the root, at index 0. This kicks off phase 2, the sorting loop. This is where we're going to systematically pull out the biggest elements and lock it into its final sorted spot. And this process is like this really elegant 3-step dance. Step 1, swap. We take that root element, the biggest one, and swap it with the very last element in our heap. Boom! The largest value is now at the end of the array, right where it belongs. Step 2, shrink. We basically just pretend the heap is one element smaller now, effectively locking that sorted element in place. And step 3, sift down. The new element we just put at the root, it's probably not the largest anymore, so we have to sift it down to restore that max heap property. And we just repeat this cycle over and over until the heap is empty and presto, the array is sorted.
So let's just visualize how the array is changing through all this. At the start, it's just a random jumble of numbers. After that super fast ON build phase, it's a perfectly structured max heap. Then, after just one swap, the single largest element moves to the very end. We just keep doing that loop n-1 times, and the whole array just falls perfectly into sorted order.
Okay, so we've got the how down. But what about the when? When should we actually reach for heap sort? Let's dive into its performance, its trade-offs, and where it really shines in the real world.
Okay, its single biggest selling point, hands down, is its memory usage. Heap sort needs only O1, or constant extra space. It sorts the array right there, in place. No extra copies. For any situation where memory is tight, this is a massive, massive win.
And when you see it lined up against its main competitors, it really puts things in perspective. I mean, look at quicksort. It can completely fall apart and degrade to ON squared in its worst case. And merge sort? It needs a whole extra array's worth of memory, ON. Heap sort kind of gives you the best of both worlds, that guaranteed ON log-on time with that beautiful O1 space. But take a look at that last column.
Yeah, that brings us to a really key trade-off, and honestly, a super common interview question. Is heap sort a stable sort? What that means is, if you have two items that are equal, will they stay in their original order after the sort is done?
And the answer is a definitive false. Nope. During all that sifting and swapping, it's totally possible for one element to leapfrog over another element that has the exact same value, messing up their original order. So bottom line, if you absolutely need stability, heap sort is not your algorithm. You'd probably want to look at something like merge sort instead.
So this really nails down heap sort's special niche, right? You pull this tool out of the toolbox when that O of 1 memory footprint is a non-negotiable requirement, or when you absolutely positively cannot risk quicksort's worst-case meltdown. It's also the engine that powers the priority queue data structure, which is just everywhere. It's vital for things like scheduling tasks in an operating system or powering famous graph algorithms like Dijkstra's.
Okay, and here's the final, really crucial piece of practical wisdom. Even with its superior worst-case guarantee, heap sort is often actually slower in practice than a well-implemented quicksort. And you might ask why? It all comes down to something called cache locality. Quicksort tends to access memory in a nice sequential line, which modern CPUs absolutely love. Heap sort, on the other hand, is always jumping around the array to get to parents and children, and that is way less cache-friendly, which costs it some real-world speed.
So you see, heap sort is way more than just a sorting algorithm. It's a tool that guarantees performance and efficiency. And understanding its principles, that doesn't just help you sort arrays. It unlocks some really powerful patterns for solving a whole bunch of other complex problems.
In fact, it unlocks a whole family of important problems, especially the kind you're going to see in technical interviews. That core heap logic, it's perfect for finding the kth largest item in a huge collection, or tracking the top k most frequent elements in a data stream, or even maintaining a running median. And that is the key takeaway here. The heap isn't just for sorting. It is a fundamental technique for efficiently managing order in a dynamic, messy world of data.